Welcome to the Deep Dive, the show that cuts through the noise to get straight to the critical insights you need to be truly well-informed. Today, we're plunging into a topic that, well, it's often unseen, rarely celebrated, but it's absolutely foundational to the integrity, the longevity of every single building around us. I'm talking about water. You know, the universal solvent, the relentless enemy of structures, and that silent, insidious threat that's constantly looking for a way in. Always testing, always seeking any vulnerability.
It really is. It's a force of nature that we often just take for granted, I think, until it's breached our defenses. Water is just an incredibly powerful element, and its ability to compromise structural integrity is routinely underestimated, often until the damage is already done, and often, yeah, quite extensive damage, too. When you consider the sheer volume of water buildings face over their lifespan, daily rain, persistent groundwater, humidity, managing it becomes this monumental, frankly, unending task.
And that's precisely where unsung heroes come in. The waterproofing consultants. These are the highly specialized experts, the true guardians, you could say, of our built environment. They're dedicated to keeping water out, quietly working behind the scenes, protecting our most valuable assets. And here's where it gets, well, really interesting and frankly a bit staggering. A leading waterproofing consultant recently revealed that a full 90% of all construction litigation is related to water intrusion.
90%, yeah.
That number alone should make us all just sit up and pay attention, shouldn't it? It's not just a statistic, is it? What fundamental flaw or maybe a persistent cultural blind spot in our construction industry does that number truly expose? Is it just lack of knowledge, or is it something deeper about how projects are budgeted, prioritized, perceived even?
That's such a crucial question. And yeah, that statistic isn't just a number. It's like a flashing red light for the entire construction industry. It really points to a systemic undervaluation of something absolutely essential. Often, waterproofing is seen as just a cost center, right? An invisible component that, when it's working perfectly, nobody notices. Nobody praises it. But when it fails, oh boy, it brings everything to a grinding halt. Project delays, massive budget overruns, even health hazards like mold. The deep insight here, I think, is that we're often designing for immediate functionality, aesthetics, without fully appreciating that resilience, longevity. They're built into those invisible layers. We tend to focus on, symptom relieving policies, reacting, fixing leaks after they appear, rather than that kind of long-term restructuring that prioritizes robust integrated waterproofing right from the start, that 90%. It isn't just about water, it's about the hidden cost of our priorities. It's a stark indicator of how often critical behind-the-scenes work just gets overlooked.
That's a powerful way to frame it. So our mission today is to cut through that noise and truly uncover why something as seemingly humble as a waterproofing layer is in fact one of the most important, yet like you said, often overlooked components of any durable, any resilient building. We're going to explore this hidden battlefield from the foundation all the way up to the roof to understand not just what keeps water out, but why it's such a persistent challenge and what it truly means for the longevity, the value of our built environment. We'll uncover some surprising facts, hopefully inject just enough humor to keep you hooked on this vital, invisible battle. Okay, let's unpack this a bit. We all know water is absolutely essential for life, right? For every living thing on this planet. But for buildings, it's a constant adversary, a relentless, opportunistic foe. It's not just that it dissolves things over time, slowly eating away at materials. It's also an incredibly powerful physical force. I mean, think about it. Water infiltrates, seeks out the tiniest crack. Then, when it freezes, it expands with this immense force. It can crack even the strongest concrete, stone. And it carries corrosive stuff too, right? Contaminants, salts, pollutants, deep into a structure's very bones, accelerating decay, compromising structural integrity from the inside out.
Indeed, it's a multifaceted attack. Buildings face this relentless assault from, well, numerous sources. Obviously, there's rain, often driven by wind, but also groundwater, just pressing in from below, and even humidity, causing condensation within building cavities. Then there's splashback from the ground, which can wick moisture up in the walls. And let's not forget, human-introduced water plumbing leaks, irrigation runoff, spills from daily activities. Vitruvius, the ancient Roman architect. In his text, he even highlighted the dangers of using earth as fill around substructures. He noted how in winter it increases in weight and bulk by taking up a great deal of rainwater, and then it bursts its enclosing walls and thrusts them out. He actually saw walls buckling and failing, not from a structural flaw, but from the relentless expansive pressure of water-saturated soil. So this problem, this relentless pressure from the very earth we build on, it's been with us for millennia.
That's fascinating, taking us all the way back to Vitruvius. It really highlights that this isn't some modern invention, this battle against water. It's a fundamental challenge our ancestors grappled with, sometimes with, well, surprisingly sophisticated insights. It truly shows the enduring nature of this threat. And it brings us squarely to the specialized world of waterproofing consultants. These aren't your general contractors or even your typical structural engineers. This is a highly specialized craft. They bring unique knowledge, skills, experience, much like, how project management guides describe people who provide specific expertise necessary for project outcomes, often in highly specialized areas demanding deep, nuanced understanding.
And what's truly fascinating here is that while this work is absolutely vital, it often goes unacknowledged, almost by design, really. When waterproofing is successful, it's invisible. Nobody sees it, so nobody praises it. Samuel Slorman, in one of his books on engineering, he touches on how engineers sometimes feel this lack of prestige and power, that the centers of power lie elsewhere. Waterproofing can definitely feel like that. A thankless task, maybe. A silent war fought in the dark. When a building doesn't leak, no one celebrates the waterproofing. They just assume it should work. It's expected. But when it fails, when water breaches the envelope and causes damage, that's when everyone suddenly notices. And the impact is profound, financially, structurally, reputationally. It's this constant uphill battle against entropy, against nature's persistent attempts to reclaim what we've built.
And the profound impact is where we get back to that bombshell statistic.
Hmm.
90% of all construction litigation is related to water intrusion. So what does this actually mean for a project, practically speaking? What are the real-world consequences when water finds its way in?
It means enormous financial and reputational risk, not just for the contractor, but for the developer, the owner, even future occupants. Water intrusion translates directly into costly claims, protracted disputes, and often, legal battles that can just drag on for years. Think about liquidated damages. That's a term that strikes fear into the heart of any project manager. For listeners who might not be steeped in construction contracts, can you explain what those are and why water intrusion is such a direct trigger?
Oh, absolutely. Liquidated damages, they're clauses written right into construction contracts. They specify a predetermined financial penalty, usually daily or weekly, that the contractor has to pay the owner for each day the project gets delayed beyond the agreed upon completion date. It's basically a pre-agreed amount to compensate the owner for losses due to delays without having to go through the hassle of proving actual damages in court. And water intrusion, as you can imagine, is a prime culprit for triggering these. Imagine a major leak that forces work to stop, requires expensive remediation, resequencing of trades, maybe even tearing out already completed work. Suddenly, days turn into weeks, and those liquidated damages start piling up fast. They can quickly erode profit margins, cause immense financial strain. It's an incentive, or maybe penalty, really, to avoid delays at all costs.
Precisely. Risk management guides emphasize early identification of risks and opportunities to lessen the impact of risk events on a project. Water is arguably the biggest, most pervasive risk out there. Other resources remind us that tens of thousands and often millions of dollars are at stake, not to mention your reputation, when it comes to minimizing project risks. These aren't abstract numbers. They represent lost time, lost money, a damaged legacy. It just underscores why getting waterproofing right the first time isn't just good practice. It's an economic imperative.
So, if the financial and reputational stakes are that high today, it makes you wonder if we're perpetually rediscovering this problem. Because, as you've hinted, this battle against water, it's far from a modern innovation, is it? We've been wrestling with this challenge for as long as we've been building things. Can you take us on a brief historical tour? How did ancient civilizations approach this enduring problem before we had all our modern membranes and fancy sealants?
Absolutely, and it's a fascinating journey. It really highlights human ingenuity in the face of nature. Even in ancient times, the Minoans, for instance, show this early, almost ritualistic engagement with water within structures. The throne room at Knossos, dating back thousands of years, had a stone-lined pit for water. It suggests a deliberate, carefully engineered design to either manage or interact with water in a deeply significant space. Whether it was for ceremonial purposes, drainage, maybe even early air conditioning, who knows? But it shows a conscious effort to integrate water management into monumental architecture. Later, the Romans, known globally for their engineering prowess, they innovated with concrete, a viscous mixture of sand, lime, and water toughened by an aggregate of rubble. They poured this into wooden formwork, and it cured into these incredibly robust, nearly monolithic, and remarkably fireproof shapes. Revolutionary stuff. But even with such a robust material, sustained water management would have been a crucial consideration over time. We know even the most impressive Roman structures, like aqueducts, eventually showed wear and tear from constant water exposure. As Vitruvius observed, even the surrounding earth, if not managed, could compromise these grand monolithic structures. So yes, the challenge has always been there, just the materials and techniques have evolved.
That's incredible. So even the most advanced builders of their time were constantly adapting to water's challenges, sometimes with methods that look remarkably similar in principle to our own. That really puts into perspective the enduring nature of this battle, doesn't it? It makes you wonder if water is simply an opponent we'll never truly defeat, only continuously manage. So if water is this relentless, fundamental adversary, how do we design to keep it out? It's clearly not just about one product or one detail, right? The experts we talk to, they emphasize that effective waterproofing is a whole system challenge. It requires this holistic view, how the entire building interacts with its environment from the ground up to form an impermeable envelope.
Exactly. This ties directly into concepts like whole system engineering. You can't just isolate one component and expect it to magically solve all your water problems. You have to consider how all parts of the building work together to resist water, and even how the building interacts with its local ecosystem, the geology, for water management. It's about layers of defense, all working in concert.
Let's start at the very bottom then, the foundation. This is truly the first line of defense against groundwater, moisture, everything rising from the earth itself. What happens when you're building on particularly challenging ground, like a soft marsh or a bog?
Palladio himself, the influential Renaissance architect. In his books, he provides some fascinating, incredibly detailed insights here. For soft ground or bogs, he prescribes using piles, whose length, he says, should be the 8th part of the height of the walls and their thickness the 12th part of their length. This isn't just about structural support. It's about creating a robust, stable base where water has less opportunity to infiltrate or destabilize. Crucially, he details that these piles must be driven so close to one another as not to leave space for others to come in between. And get this, with blows frequently repeated rather than such as are violent, that so the earth may bind the better to fasten them. This meticulous attention to driving piles, it demonstrates a deep historical understanding of how to stabilize a foundation and resist groundwater pressure, creating a dense, almost impermeable barrier in the ground itself.
That's incredibly specific advice from centuries ago. Wow. And it speaks to the fundamental challenge of building on uncertain ground. Beyond just structural support, what about managing moisture under concrete slabs, especially in modern construction?
Modern construction uses very specific strategies for this. For structures like, say, externally insulated monolithic slabs, builders use protective membranes. These act as capillary breaks and drainage layers.
Okay, capillary breaks, that sounds like a very specific piece of engineering. Can you walk us through what's happening there? How does water manage to defy gravity? And what exactly is a break doing?
Absolutely. Think of it like a sponge, maybe, or even the way a paper towel soaks up a spill. Water has this amazing ability called capillary action to wick upwards through tiny pores and spaces in materials, even against gravity. So if your concrete slab is directly on the ground, moisture from the soil can slowly, relentlessly climb up into the slab itself. That leads to dampness, mold, damage inside the building. A capillary break is a layer after its granular material like coarse gravel, or maybe a specific type of durable membrane with pores that are just too large for water to climb effectively. It literally breaks that capillary path. It acts as a barrier to prevent ground moisture from wicking up into the structure. You couple that with a drainage layer, which helps divert any bulk water away, and it's a pretty solid dual defense for your foundation.
Right, makes sense.
Exactly. And for something like a garage slab, it's common practice to include a polyethylene vapor barrier under slab, combined with that granular capillary break and drainage pad to manage moisture. This prevents ground moisture from wicking up into the concrete and eventually the building interior. These seemingly simple layers, they're vital for keeping the slab dry and preventing future issues.
And it's not just about keeping the building dry, but safe, too. I recall reading how foundation sealing is also linked to protecting occupants from environmental hazards, specifically radon, that gas we can't see or smell.
That's a critical connection, yeah. Radon, it's colorless, odorless, radioactive gas naturally produced by the decay of radium in the soil and rocks beneath our homes. While it's inert itself, its decay products, known as radon daughters, are not. If you inhale them, they can attach to lung tissue and significantly increase the risk of lung cancer. Scary stuff.
Radon mitigation systems fundamentally rely on creating a sealed barrier against the ground, much like waterproofing does. It prevents these harmful gases from entering the building. So the integrity and sealing of your foundation literally protects the air you breathe inside. It's an invisible shield not just against water, but against a silent environmental threat.
Okay, moving up from the foundation then, the walls. The next critical barrier in our impermeable envelope. How do we secure these large vertical elements against water, considering they're constantly exposed to the elements?
The fundamental principle, especially in climates that experience, significant temperature swings or dry periods, is to protect building assemblies from getting wet from the exterior and allow it to dry towards the interior. This is a really crucial concept. It means installing things like air barriers and vapor retarders on the exterior to prevent water and moist air from getting in, but then using permeable interior wall finishes to allow any moisture that does somehow get in, or maybe condensation that forms, to dry out safely towards the inside without causing damage. It's all about directional drying, making sure the building breathes in the right direction, so to speak.
That makes profound sense, letting the building manage moisture dynamically. I've heard about fluid-applied systems for walls. They sound a bit like painting on a shield. How do those work? What are their advantages?
You've got the right image, pretty much. Fluid-applied waterproofing provides this comprehensive, seamless barrier. It's literally sprayed or rolled over cement, board coating the entire surface, ensuring that the exterior walls or even complex interfaces like where a shed roof meets a wall are fully covered. The advantage of a fluid-applied system is its monolithic nature. It conforms to every curve, corner, penetration without any seams. Seams are often the weakest points in sheet-applied membranes. So this creates an incredibly robust, impermeable layer that adapts to irregular shapes much better than some preformed sheet goods. That makes it ideal for complex architectural designs.
So it's about making sure there are absolutely no gaps anywhere. But what about all those tiny places where different materials come together, like at the very bottom of a wall where it meets the floor or around windows? Those seem like natural weak points.
Oh, those are precisely the critical junctions. That's where meticulous attention to detail is just paramount. That's where elements like sill gasket, sealant, adhesive, or gasket on top plate and bottom plate at exterior become absolutely crucial. Similarly, applying sealant at the corner of the bottom plate and subfloor or gasket under the bottom plate, that creates a continuous air and moisture barrier at these vulnerable junctions. These aren't glamorous details, often hidden, but they're absolutely essential for preventing both air and water infiltration that could compromise the entire wall assembly over time. They're kind of the unsung heroes of the wall system.
And I've come across this term bond breaker in some of the materials. It sounds almost counterintuitive. Why would you want to break a bond, especially when we're talking about sealing things up? Can you shed some light on that?
That's a great question, and it really highlights the nuance in waterproofing. A bond breaker is actually a strip of material, often just a thin plastic film or tape, that the sealant does not stick to. It's strategically placed in a joint, for example, at the back of a sealant bead to prevent what's called three-sided adhesion. See, if a sealant adheres to all three surfaces of a joint, both sides and the back, its ability to stretch and contract as the building moves, due to temperature changes, settling, wind loads, that ability is severely compromised. It gets pulled in too many directions, leading to premature tearing or failure of the sealant. By using a bond breaker, you ensure two-sided adhesion. That allows the sealant to flex freely, more like a diaphragm, maintaining its elasticity and optimal long-term performance. It's a small, invisible detail that makes a huge difference in the longevity of a seal.
Fascinating. A tiny detail with such a critical function, and even outside the immediate wall, managing runoff is key, right? Especially from the roof. I always picture those ancient gargoyles spitting water far away, very dramatic, if somewhat unsettling form of splashback prevention.
A very effective, albeit dramatic form, indeed. We often talk about splashback, which is literally water and soil getting deposited on an exterior wall near the ground by roof runoff splashing off the surface below. This can lead to staining, erosion, even moisture problems at the base of the wall. To counteract this, we use splash blocks, simple, angled concrete or plastic pieces placed at the bottom of downspouts. They divert water away from the foundation and walls, preventing localized damage and erosion. It's a simple, low-tech solution to a very common and persistent problem. Just ensuring that the water shed from the roof doesn't become a problem for the walls and foundation below.
All right, let's climb to the top of the building. The roof, our overhead shield against the sky. How do waterproofing strategies change up there, especially for those ubiquitous low-slope designs we see everywhere?
For low-slope roofing assemblies, the roofing membrane itself, whether it's TPO, EPDM, modified bitumen, whatever, often can act as a vapor retarder. This is crucial to understand. However, a critical caution is against the possibility of entrapping moisture between these two impermeable layers if you improperly include an additional vapor retarder in the assembly. This decision is very much case-dependent. It requires careful consideration by an expert to avoid creating a moisture trap within the roof assembly that can lead to blistering, material degradation, and ultimately, failure. It's a complex dance of layers up there.
So sometimes less is more when it comes to layers if they're not designed to work together perfectly. Interesting. What about traditional wood roofs like shingles or shakes? How do they handle moisture given they're not monolithic membranes?
Traditionally, wood shingles and shakes were installed over skip sheathing or spaced sheathing. These are basically spaced boards running perpendicularly across the rafters rather than a solid plywood deck like we often see now. This practice allows for airflow underneath the shingles, which is vital for moisture removal and preventing decay in the wood itself. Wood is organic, right? It needs to breathe and dry out. This clever, low-tech method of allowing air circulation was a time-tested way to ensure the durability and longevity of wood roofing systems. It prevented rot and extended their lifespan significantly.
That's a great example of an ancient solution to a persistent problem, one where the material's properties are deeply understood and accommodated in the design. And metal roofs, they look so sleek, almost minimalist. But what's the ingenious part of their water tightness? How do those raised seams really work to keep the water out?
That's a great observation, and the genius of a standing seam roof lies precisely in its elevation and connection method. Unlike a traditional shingle roof where fasteners often penetrate the waterproofing plane, standing seams lift the critical connections above the plane of the roof. Imagine interlocking metal panels that literally stand up, creating a raised ridge or seam where they join. Water just flows down the smooth panels and efficiently sheds off the roof. It never encounters an exposed fastener or a flat, vulnerable seam. The mechanical interlock ensures not only superior water tightness, but also incredible resistance to wind uplift, as the fasteners are often hidden beneath the panels. It's a design where the very aesthetic contributes directly to its waterproofing strength, a true blend of form and function that epitomizes resilience. Okay, moving inside the roof assembly now. Attic ventilation sounds crucial. How does that play into moisture management, and what about those notorious ice dams we hear about in colder places? Attic ventilation is absolutely essential to remove moisture from roof assemblies and to control ice damming in colder climates. Yes. It works by creating a continuous flow of cooler outside air through the attic space. This helps keep the roof deck temperature uniform. This even temperature prevents snow on the roof from melting prematurely, then refreezing at the colder eaves and forming those destructive ice dams. Ice dams can force meltwater back up under shingles, leading to severe leaks. Ventilation is most effective when half the vent area is near the ridge and half is near the eave, creating that crucial crossflow. However, it's important to note that in certain climates, a separate vapor retarder is actually not recommended in vented roof assemblies. The ventilation itself is designed to manage moisture, and adding another impermeable layer could inadvertently trap moisture. It's a delicate balance that relies heavily on local climate conditions.
It seems like Frank Lloyd Wright had an intuitive understanding of roof protection, too, integrating it into his design philosophy as a fundamental aspect of his architecture.
He certainly did. Wright famously used broad protecting roof shelters as a core design philosophy for his prairie-style homes. This wasn't just aesthetic. It intrinsically integrated passive weather protection into the architectural form itself. His deep, wide overhangs shielded walls and foundations from direct rain, snow, even harsh sunlight. This inherently contributed to the building's durability and reduced the workload on the more technical waterproofing layers. It's a prime example of design foresight, really, how architectural form can inherently contribute to a building's resilience against the elements.
We've talked about the big picture, from foundation to roof, and how these systems are designed to work. But here's the really critical insight, the one that our waterproofing consultant emphasized. Most leaks occur not in the middle of a system, but at the transitions, penetrations, and terminations. What makes these spots so incredibly vulnerable? Why isn't it the broad, flat surfaces that usually fail?
This is truly the devil in the details for waterproofing, and it's where the most costly failures almost always originate. These are the points where continuity is hardest to maintain, where different materials meet, where forces, both internal, external, like thermal expansion and contraction, tend to concentrate. It's incredibly difficult to ensure a perfect, unbroken barrier when you have, say, a pipe going through a wall, or two different types of cladding meeting at a corner, or a roof membrane ending at a parapet wall. Any small mistake, any overlooked detail, any lack of precision in these junctions can lead to catastrophic failure. It acts like an open invitation for water. The broad, flat surfaces, they're usually manufactured pretty consistently, but it's at these complex, custom-fitted edges and breaks in the surface where the human element, and thus the potential for error, is highest.
That makes perfect sense. So let's dive into penetrations, for example. I can see how anything that breaches the building's otherwise solid envelope would be a natural weak point.
Exactly. Building codes require that penetrations be protected to maintain the fire-resistive integrity of the assembly being penetrated. We need to apply a similar meticulous logic to waterproofing, ensuring an uninterrupted barrier around all elements passing through it. Think about the myriad of common penetrations: pipes for plumbing or HVAC, electrical conduits, structural elements like beams or anchors, and especially windows and doors. They all breach the envelope, creating potential pathways for water.
And chimneys are a classic example of a complex penetration, aren't they? They're often large, sometimes hot, and cut right through the roof and maybe a wall, too.
They absolutely are. Best practice actually suggests installing chimneys within the interior of the building enclosure to protect them from external weather exposure as much as possible. If they must be on an exterior wall, then chimney enclosures should be insulated full height to keep chimney flue pipes warm to ensure sufficient draft. This internal placement and insulation helps manage condensation within the chimney itself, prevents thermal bridging where heat escapes or enters, leading to internal moisture issues, and most importantly, it minimizes the number of complex exterior penetrations. That makes it easier to maintain a continuous waterproof barrier around it.
And what about something as seemingly minor as a floor or ceiling boot, where ductwork passes through a floor or ceiling? I wouldn't instinctively think of that as a major water ingress point from the outside.
You're right, it's not typically a direct water ingress point, like a foundation leak from rain. But these areas are absolutely crucial for air and vapor sealing, and that profoundly impacts internal moisture management and overall building performance. Some guides note the need for specific air sealing at floor boot air sealing and ceiling boot air sealing, using things like mastic and fiberglass mesh at the joints. This meticulous sealing is crucial because these areas experience greater local vibration and flexure just from the movement of air through ducts and even general building settling. That movement can compromise a seal over time. It vividly illustrates how meticulous attention is needed even at these small, seemingly insignificant points for overall building performance, preventing air leakage that carries moisture and compromises thermal efficiency.
That's a great example of how a tiny, seemingly insignificant detail can have outsized consequences, impacting comfort, energy efficiency, potential moisture issues. It reminds me of a cautionary tale I heard, almost a metaphor, about a plumber falling through an unprotected opening on a floor deck.
Yes, that anecdote is a powerful parallel. It describes how an unprotected opening, a small detail, a hazard that was overlooked or maybe deemed minor, can lead to catastrophic consequences, in that case, a fatality. In the very same vein, a tiny, underdressed gap in waterproofing at a penetration, even one meant for something as simple as a floor boot or a window, can lead to massive, multi-million-dollar damage over time. It's about recognizing that small vulnerabilities, when ignored, can become the sources of major, devastating failures. The principle of diligent protection applies right across the board.
So let's talk about windows themselves. They're one of the most common and complex penetrations in almost every building. What does it take to waterproof a window effectively?
Window openings are indeed critical penetration points, a real symphony of different materials converging. For, say, an ICF recessed windowsill stucco assembly, the detail requires multiple, carefully integrated layers. You might start with a primary sealant around the frame, often resting on a precast concrete sill for structural support and water shedding. Beneath that, you might have a backer rod and sealant to ensure proper sealant geometry and adhesion. And then finally, a continuous membrane waterproofing layer that ties seamlessly into the wall system. This layered, redundant approach is necessary because a window is where all these disparate materials and systems, glass, frame, wall, sill, all converge. Each needs a continuous watertight connection that can also accommodate movement. It's a masterclass in detail, really.
So it's not just penetrations, but also transitions and terminations where one waterproofing system ends and another begins that are the real trouble spots. That's where all those different materials meet, right?
Precisely. This is where one waterproofing system or material meets another, or where a system simply ends. For example, a roof membrane terminating at a vertical wall, or a flashing detail around a skylight. Continuity is easily broken at these interfaces because they are inherently complex. This is why flashing is so essential. Things like flashing ledger nailed over top of rigid insulation ensure a continuous drainage plane and proper water shedding. They direct water away from the vulnerable wall assembly beneath. It's all about creating a seamless transition, even when materials are inherently different and have different properties, ensuring the water is always directed out and down.
And often these tricky points become compromises during construction because of budget pressures. I'm reminded of that classic anecdote from the Bookhouse. It speaks volumes about real-world tensions.
Ah, yes, the Cadillac versus Chevrolet dilemma. The contractor observed that the guy wants to build a Cadillac and they only want to buy a Chevrolet. This perfectly illustrates that real-world tension between desired quality, which might mean thorough, redundant waterproofing at every complex transition with premium materials, and the relentless pressure of budget constraints. When corners are cut, it's almost invariably at these complex transitions and terminations that compromises are made, because they're often out of sight, and they appear as extra cost. These compromises, unfortunately, become future failure points, and the source of so much of that 90% litigation statistic. It's a classic trade-off where short-term savings lead directly to long-term costs.
So how do we push past the Chevrolet mentality and ensure we build buildings that truly last, that are resilient against the inevitable assault of water? It starts with best practices, and first on the list seems to be designing for redundancy, creating multiple layers of protection.
That's right. True resilience in waterproofing, much like in nature or in robust engineered systems, doesn't rely on a single perfect barrier. It comes from having multiple overlapping layers, each acting as a backup for the other. Think of tough materials like metals, wood, even biological materials. They contain elaborate defenses against the effects of stress concentrations and cracks. A single crack in one layer doesn't mean immediate failure if another layer is there to catch it, deflect the water, or slow its progress. In waterproofing, this means designing with multiple barriers, drainage planes, redundant seals. So if the first line of defense is breached, there are still 2 or 3 more to prevent water from actually getting into the occupied space.
So it's not just one membrane, but a whole system of defense, like an onion with many layers. But doesn't building in all that redundancy come at a significant cost? How do you balance the desire for ultimate protection with the realities of a project budget? It's a delicate balance, absolutely. And that's precisely where that Chevrolet versus Cadillac dilemma often comes right back into play. Yes, redundancy adds cost upfront, more materials, more skilled labor, more complex detailing, no question. But if you look back at that 90% litigation statistic, the cost of not building in that redundancy is just astronomically higher down the line. It's an investment in resilience, much like buying insurance, really. You pay more upfront to avoid potentially catastrophic losses later. A truly informed client understands that the cost of proper redundant waterproofing is just a fraction of what a failure will cost in repairs, legal fees, mold remediation, reputational damage, tenant displacement. The list goes on. It's about shifting from a short-term, lowest bid mentality to a long-term best value perspective, acknowledging that this initial investment buys decades of peace of mind and structural integrity.
That clarifies it beautifully.
Mm-hmm.
So beyond having those layers, it seems crucial that we can actually verify they're doing their job before they're covered up and out of sight forever. That's where inspectability comes in, right? Designing so you can actually see the invisible.
Absolutely. If you can't inspect a system, you can't truly guarantee its quality or performance. It's that simple. This requires thoughtful design that allows access for quality control throughout the installation process, and definitely before anything gets covered up permanently. Construction management standards emphasize quality management and the construction manager's role in monitoring contractor compliance. If non-conforming work that just doesn't meet specifications, is discovered, there must be clear procedures for notification, correction, even stopping work until it's rectified. For waterproofing, this can include rigorous testing like flood tests for horizontal surfaces like plazas, balconies, or roof decks before they're concealed. Literally filling the area with water for a set period and watching meticulously for leaks to ensure water tightness.
That makes perfect sense. You can't fix what you don't know is broken, and it's far, far cheaper to fix it before it's hidden behind finishes. And this brings us to smart, proactive planning, especially with modern digital tools like building information modeling or BIM. How does BIM bridge that historical gap between design and construction to dramatically improve waterproofing quality?
Oh, BIM is a revolutionary game changer for complex building systems. Historically, as the BIM handbooks point out, there was this professional gap between designers and builders that became really pronounced during the Renaissance. Complex systems relied on often misinterpreted 2D drawings. BIM directly addresses this by creating a collaborative, information-rich 3D model,
All project participants, architects, engineers, contractors, specialists like waterproofing consultants can share information in real time. It facilitates just unprecedented communication and moves way beyond traditional 2D drawings and specs. It makes it infinitely easier to visualize, coordinate, and understand complex waterproofing details from every single angle.
And one of BIM's most powerful capabilities is clash detection. That sounds like it could save a lot of headaches in a waterproofing context, catching those errors before they become multi-million-dollar problems.
It's incredibly valuable, almost like having a crystal ball that predicts problems before they happen. Traditionally, clash detection was done manually by overlaying 2D drawings on a light table, which was, slow, costly, prone to error. BIM, however, excels at automatically detecting clashes between drawing entities. It can identify hard clashes, where objects physically occupy the same space, like a pipe going directly through a structural beam. Ouch. Or soft clashes, where objects are too close for adequate access, maintenance, or proper insulation. That could impede proper waterproofing installation or repair down the line. Identifying these conflicts early in the design phase, long before a shovel even hits the ground, is absolutely crucial for preventing costly rework and ensuring the integrity of complex systems like the building envelope.
So it can catch those tricky penetrations or tight transitions before they even become an issue on site. And what about design for fabrication? How does that tie into improving quality, especially for critical systems like waterproofing?
BIM also enables design for fabrication, which basically means producing reliable and error-free information that allows for the prefabrication of complex building subassemblies off-site in a controlled environment. For instance, highly complex facade or curtain wall systems, which are heavily reliant on perfect waterproofing, can be fabricated in a factory setting with much higher precision and quality control. Then they're just brought to the site for assembly. This reduces costs, increases quality, and simplifies the construction process, especially for systems where precision and consistency are paramount, like the building envelope, where even a millimeter of error can eventually lead to a leak.
And all this proactive planning and error reduction with BIM must have significant financial benefits, right? Beyond just avoiding litigation.
Oh, absolutely. The financial benefits are substantial. By enabling issue discovery and problem identification to occur early and more frequently, BIM allows teams to resolve issues early. That's when changes are cheapest and easiest to make. This significantly reduces the financial impact of rework, change orders, delays, and of course potential litigation related to failures like water intrusion. It's about investing a little more upfront in intelligent design and coordination to avoid massive, unforeseen costs and headaches down the line. It basically shifts risk from the unknown to the known.
We've laid out the best practices, the ideal scenario for designing and constructing resilient buildings. But sometimes, despite all the knowledge and technology available, corners inevitably get cut. And when that happens, especially with something as critical and unforgiving as waterproofing, the consequences can be truly disastrous. It's not just a small inconvenience. A single, poorly executed detail can lead to multi-million-dollar failures.
It's a harsh reality that we see play out repeatedly in the industry. Yeah, the upfront investment in quality waterproofing and expert consultation often seems negligible when compared to the astronomical costs of remediation, legal fees, reputational damage, even health issues that result from a single failure point. It's penny-wise and pound-foolish on a truly grand scale.
We don't have to look far to find historical examples of water's destructive power where humans fought against seemingly insurmountable odds. Mark Brunel's Thames Tunnel project. That's a perfect cautionary tale on a truly grand scale, a battle against water that nearly broke its creators.
Oh, that project was just a monumental, heroic, and ultimately terrifying struggle against water. As the biographies detail, the tunnel faced extraordinary difficulty and delicacy. Due to soft and treacherous ground beneath the river, the river broke into the tunnel on no less than 5 occasions. Not just once, 5 times. Each incident threatening to drown the workers and halt progress indefinitely. The atmosphere became even more lethal than before. Men collapsed in the frames. Sewer gas would suddenly ignite. It created this incredibly dangerous and unhygienic environment. This vividly illustrates the relentless and dangerous nature of water intrusion on a grand scale, and the sheer persistence, often at great human and financial cost, required to overcome it. It was a project that redefined what was considered possible, but yeah, at immense human suffering.
Talk about a high-stakes battle. And even on smaller, more common projects, a lack of foresight and attention to detail can create massive, avoidable costs. I'm thinking of that red flagging oversight for the special Italian marble tile.
That anecdote is a perfect, almost painfully relatable example of how detail-oriented planning prevents massive cost overruns. An inexperienced estimator failed to red flag a special Italian marble tile that had an astonishing 6 months lead time. 6 months. When the project neared completion, it was realized the tile wouldn't arrive in time for the grand opening. Disaster. To avoid liquidated damages for a delayed opening, a stock tile was temporarily installed, then meticulously removed months later and replaced with a specified tile. The entire cost chalked up as a loss. This lack of foresight, this failure to highlight a critical path item, mirrors how a seemingly minor omission in waterproofing planning, maybe a decision to use an unproven material or just a lack of detail in a drawing, can lead to systemic failures and exorbitant costs later on. It's all about anticipating and planning for those critical details.
So it's a direct parallel. Don't overlook critical items, whether it's marble or a crucial waterproofing membrane, because the cost of fixing it later is almost always exponentially higher. And speaking of cost, there's always the temptation to go with the lowest bid for subcontractors. But that can be a dangerous trap, can't it?
It absolutely can be. And it's a constant challenge in the construction industry, especially with complex, invisible systems like waterproofing. Project management books discuss the inherent risks associated with selecting very low-bid subcontractors who probably omitted some item of work and will not be able to complete the job to meet that low price. This inevitably leads to additional costs to complete the work and significant impacts on work progress of the entire project. When a subcontractor cuts corners on waterproofing to win a low bid, maybe using cheaper materials, inexperienced labor, skipping critical steps, those systemic failures will inevitably cost the project far more in the long run than any initial savings. It's just a false economy.
And then there's the broader issue of prioritizing speed and cost over quality, often seen in large-scale public work projects where maybe political will can override engineering prudence. Robert Moses's projects in New York come to mind. The emphasis was often on sheer output.
Yes, Robert Moses, as described in The Power Broker, often prioritized simple designs and cheap materials rather than architectural excellence. He was a master of efficiency and delivery, sometimes, at the expense of long-term quality. He sometimes lacked adequate engineering assistance for certain projects and had to, plead with the WPA for approvals for even small amenities. While he delivered massive projects quickly and under budget, his approach meant that when his direct personal oversight was absent, the projects were often less distinguished and less durable. This perfectly illustrates how political or economic pressures can undermine crucial, often invisible quality, like proper waterproofing and robust material selection, leading to less durable outcomes, even if they meet immediate budget and schedule demands. The legacy of those compromises often lives on in maintenance and repair bills for decades. #outro.
What an incredible deep dive into the invisible guardians of our buildings. It's just abundantly clear that waterproofing consultants and their specialized expertise are absolutely essential, underpinning the durability, the resilience, the long-term value of every structure we inhabit. Even if their critical work largely remains out of sight, beneath the finishes, within the walls, under our feet.
It truly is about shifting our perspective, I think. Instead of merely applying symptom-relieving policies when leaks inevitably appear, which is the reactive approach, we need that long-term restructuring that prioritizes robust integrated waterproofing right from the outset. The true costs of neglect, those silent compromises made at the start, they're hidden until it's far too late and often far too expensive to rectify without major intervention.
That's a powerful thought to leave you with, and one that resonates beyond just buildings, I think. Given that water will always find a way, tirelessly seeking the weakest link, how can we foster a building culture where this long-term, invisible battle against it is valued as highly as the most visible and aesthetic elements of our architecture? And I'd challenge you, our listener, to consider this. What seemingly minor details in your own environments, whether it's your home, your workplace, the infrastructure around you, might be guarding you silently from relentless threats that you never even notice? What hidden systems are keeping your world together, and what would happen if they failed?
A truly great question for reflection. It reminds us that true resilience is often built into the unseen. Thank you for joining us on this deep dive into the fascinating, critical world of waterproofing.
Indeed. We hope this exploration gives you a new appreciation for the hidden heroes and the critical layers that protect the spaces we live, work, and thrive in. Until next time, keep digging deeper.